Objects that are stationary or moving in a straight line at a constant speed are in what's called mechanical equilibrium. We're going to talk about that in more detail. And in order to change their motion, you have to exert a force. This is what I was saying before about a net force. In other words, if you're going to push on something here and there's no force pushing in the other direction, this object will move. Okay? If there's friction, doesn't stop it, but the object will move. But that's because there's a net amount of force. In other words, you add up the forces, you say, well, there's gravity pulling down, there's the floor pushing up on this, so they balance, but this one doesn't get balanced, so it has to, the object has to move. All right, this is what Isaac Newton was the first one to figure out. Let's see, we're going to do this? Yes. Good. Okay, and as we mentioned before, I talked about with the T here that the table and gravity are, the forces that you get from that are equal and opposite. But I want to point out to you here, if you have a 10 Newton force and a 5, now Newton is that is the unit that we use for force in the international system. Okay, it's the Newton. And it's just easier to write Newton or capital N instead of writing all the other base units that make it up. So a Newton is roughly, let me see, there's almost 5 of them for 1 pound. Okay, so there's sort of a relationship there, but you don't have to know that. Just want to give you a feel for it. So, but in this case, if you have a 5 Newton force and a 10 Newton force, and they're both pushing in this direction, all right, then that means the net force is going to be 15 in this direction. All right, that's all I wanted to show you with this slide. If you have 10 pushing this way and 5 pushing that way, you're going to have a net of 5. Do you all see that? I just want you to grasp what I mean when I say net force. It's you're adding them up, right, and when you add them up, you know, in this case, you're going to be subtracting them. Okay, you're going to end up with a net force in one direction or the other. Or you're going to have a balanced force. Right? Does that make sense to everybody? Okay. You guys got this on the canvas, right? Okay. We talked about springs before with Mr. Hook, but the thing is here, I just want to point out to you that when you have something motionless like this, again, the forces on it are balanced. You have gravity pulling it down, and you have the tension in the string or the wire or whatever's holding it up. Those two are equal and opposite, just like this, right? Equal and opposite forces. And of course, the scale is built so that it will tell you what the, how much force is in the wire or in the string. I did want to mention, I don't know, we'll use this very much in class, but when you use a pulley, all a pulley does is it just changes the direction of a force. It doesn't change the force itself, it just changes its direction. So, if I wanted to lift something up from the floor there and I had a rope around it and then a rope around a pulley here, if it weighed 10 pounds and I want to lift it, I have to pull this way 10 pounds. All right? All we did is change the direction of it. That's all that force to lift it up. Okay? And a seesaw. All right, well, let's see. There are a couple of things involved here. One of them is torque, but we'll talk about that later. But in this case, I want you to realize that on the seesaw, if you have 2 people sitting there, you have the weight of the board, I want you to realize that all of the forces at that pivot point, right, where the wood is rotating, all right, all of those forces have to be supported by that one point. All right? Whatever weight you have on one side and whatever weight you have on the other side and whatever weight the board is, all of that is in the down direction. So if the board's not going to break and these people, aren't going to come crashing to the ground, all right, that means that at that one point, you have to be able to support all that weight in the up direction. I just want to hear, just because the people and the board and they're sort of spread out, it doesn't matter. If the only connection to where there's an upward force is in the middle, that's got to support everything. Okay, does that make sense? Okay. Or here, if you have 2 people on a scaffold, and let's say they're painters or window washers or something like that, and they have cables going up to the top of the building, there's a video that I can't show you because We don't use VCRs anymore. I'm not the new to get it on the DVD. It's $1,800. I don't have that much money to spend. But in any case, there's a guy that was talking about this, how he began to learn about physics, where he and this other guy were painting a building, you know, high up in Boston, and they're working together painting, and the older guy, you know, was saying something, and I guess the younger guy, who's the one telling the story, couldn't quite hear him because I guess there was a lot of noise with the traffic and all, and he sort of walked over to him and said, what? And the older guy said, whoa, you stay over there. I'll just talk louder, all right? Why did he tell him that? Because can you see that if this person walked over here, you'd have a lot more tension being held up by this cord or this cable as opposed to this one, and you know, you could get it to, you know, it would be dangerous. But again, those two are supporting the, you know, those two people. Okay? Yes, sir.
So the person standing on like the piece of wood.
In here? This
Yeah.
one? Yeah.
So if he weighed 100, would like the weight be split like 50-50, or would it be 100 on each side?
It'll be it'll be 100 altogether, but how it's actually split will just depend on, you know, on where he stands, you know, for example. And it also has to support the wood as well, the two of them. That's right. So, but just so you know that these things, you know, like I weigh 180 pounds, so if I'm hanging by 2 rings, okay, from the ceiling, okay, so if I'm 180 altogether, how much is each of the ropes supporting? 90, right? It'd be half, right? That's all I wanted you to get from this. Okay. Okay. Now, talk about the difference between a vector and a scalar. Because these are terms that you'll hear a lot of, and they actually make sense. It's just if you haven't used them before, I think you'll see that they're really not complicated. A scalar is something that's just a number, a size. You know, for example, I give an example here: 60 miles an hour. 60 miles an hour. Right? You guys have a feel for what 60 miles an hour is, but we didn't say what direction we were going. Right? So that's because without having any direction, it is just a number. You know, it's an amount, a size, a weight, whatever. In this case, a speed. But if we say 60 miles an hour south, now we've made a vector out of that. Because now we said, not only do we know that it's 60 miles an hour, but we know the direction that it's going as well. Okay, so a vector has, sure, it has a magnitude, a size to it, but it also has a direction. No direction, then there's no, it's not a vector anymore, okay? It's just a scalar. You guys see the difference between the scalar and the vector, okay? It has to have direction. Okay, then, here, what about this question? There's a Category 6 hurricane in the Gulf. It's moving at 15 miles an hour, and this is the picture you see. Should you be worried? What do you think? Time to put the shutters down? You hear that? It's going 15 miles an hour, but we didn't say what direction. Maybe it's going to Corpus Christi, right? Give those guys a hard time, right? If it's going over that way instead of this way. So I just want to point out to you how the size, you know, is important, but also you need to know the direction. Now, of course, when we look at these hurricane plots on the television, you know, or on your cell phone, they always give you the projected. They model it, right? They give you where the model projects it to go. So you know that. Okay? Then, okay, now vector, using vectors, the math can be different because of those directions. It messes you up. You know, 2 apples and 2 apples, well, since we're only dealing with apples, we're talking about just a number, all right? It's going to be 4 apples, all right? There's no way around that. But if 2 pounds of force and 2 pounds of force are added together, it can be different. Remember what we saw on that earlier slide? Depending on whether you're pushing against yourself, right, or you're pushing in the same direction, all right, they can be very different, right? In the same direction, you can double, right, the amount of force. 2 and 2 or 4 pounds of force that way. But if they're going in the opposite direction, 0, right? Because just like this thing is sitting on the table, zero force because they balance out. And if one of them is at an angle, well, then it can be any number, okay? It can be any number in between the two values there. So it gets more complicated. We're not going to do a lot with that, but I just want you to understand conceptually the difference between scalars and vectors, okay? Scalar being just a number, a size, but the vector having that direction associated with it does change things. There's a vector that we use, we're not going to use it in this class, but we use in physics called displacement, and it's where you're adding vectors. And for example, the distance, if I walk, say, from here to the end of the desk here, let's say I've gone, I don't know, what would that be, like maybe 15 feet, right? So I could say, all right, I've gone 15 feet in that direction, okay? So I can make a vector out of that. But now if I turn around and I walk, say, back to here, not quite to there, let's say I've gone 12 feet, all right? Now you would say, all right, the distance that I went is the scalar, and that's going to be 15 and 12, right, or 27. But when you add those two together, right, the vector value of it is only going to be this little bit here. That's all. Just going to be a little bit. If you don't get that, don't worry. It's just some people, it'll make that help them understand a little better how that works. But okay, we're not going to do a lot of math, so I don't want to do too much of that. Okay, mechanical equilibrium. It's when you have no net force, like we talked about, this bottle on the table, but you can also have something that's moving in a straight line at a constant speed. And that is also in mechanical equilibrium. It's called dynamic equilibrium. But the point is that when you add up the forces, this is just a capital S in Greek for standing for summation. But when you sum up all the forces acting on it, if they equal zero, there's no net force on the object. Okay, no net force in that case. That's Newton's first law, actually. His first law was when there's no net force acting on the object, it's in equilibrium, and it's either not moving, or if it's moving in a straight line at a constant speed. Because in order to deviate from a straight line at a constant speed, to go into a curve, for example, you have to exert a force. Right? If you want to accelerate or decelerate, change your speed. All right, now you have to exert a force, whether it's tires on the road or your brake pads. You're going to have to exert a force somewhere. Okay, so no net force. All right, that's Newton's first law. Sum of the forces equals zero. And I just wanted to give another example here about. We sort of talked about this a little bit with the scaffold, but if you're standing on a scale and you weigh 100 pounds, or two scales really, a foot on each one, and you're even with that, then of course the scales are going to read 50 and 50, right? But then when you lean over to one side or the other, can you see how the scales are going to change their reading? But the sum will always be the 100. You see that? All we're doing is just shifting how we're getting to that 100. That's all. And of course, if you just stand on one, then you will have 100. So, is this okay? Is this clear to everybody? All right. So the object can be stationary, and that's called static equilibrium. If the object is moving in a straight line and at a constant speed, it is also in what they call dynamic equilibrium. In this case, it would be like you're going on a road you set your cruise control, and you're going on a straight road, okay? And so the car is just going straight ahead. It just means that the force of your car pushing on the road, okay, pushing you forward, and you're burning gasoline for that, you're getting energy somewhere for that, that is exactly equal to the frictional force acting in the other direction. The forces are equal, they're balanced, just like this, as long as you're going in a straight line. As soon as you deviate from the straight line, it's no longer true, but if you go in a straight line, and the friction force is not just the bearings and the gears and the tires on the road, but mainly the wind blowing against the car. All these resistance forces are what you're fighting. But now if you were to change your direction, You know, say you turn the steering wheel, you're going to go around a curve, your car has to accelerate if you have it on cruise control. You may notice that sometime if you're going on if you have cruise, say you're on I-75 going north and you want to go around the bend to, let's say you're going to go over to St. Pete, okay, you know, they have a big curve you go around there where you can go around that curve at like 60 miles an hour. Well, if you set your cruise at 60 miles an hour and you watch your tachometer, as soon as your car starts to go around that curve, you're going to see the tachometer pick up, okay? Because the car knows if it's not going in a straight line, it's got to exert a force on the road to push it sideways, and that's going to burn more gas. So this is one of the key things that Isaac Newton figured out about motion. And his point was, when you don't have balanced forces, that means you will have a net force. If you have a net force, you must have an acceleration. That's Newton's second law. There's no exceptions to that, none at all. But I think that's probably on the next slide or shortly. No, this is just, I wanted to point out to you here about if you have something that you're holding up, you know, like I gave you the example of hanging, you know, like this, but now if we begin to move those ropes out further and further, all right, so it looks like this, all right, I want you to realize that the weight acting down is still the same. So that means you have to have the same force acting up or else you fall, okay, or the ropes break. So in that case, the tension in each of those ropes has to get higher and higher. Right? It's going to get stronger and stronger because the tension can be resolved into, let's take the one on the right here. If it's going up at that angle, that means you have some of that tension is acting in the vertical direction, but some of it's acting in the horizontal direction also. But the vertical direction has got to be half of this weight on this side and half on the other. Otherwise the object will fall. So it turns out that you develop a lot of tension in these ropes. I don't want to go into a lot. We're not going to do any of this diagonal stuff. You have some problems in the book about like that, but I'm going to skip them. I don't know. You guys are going to be doing enough math, so I'm going to skip that. But I did want to point out to you that as you move out here, okay, you still have to be able to support this amount of weight in that direction. So that means you're going to have a greater and greater amount of tension there. And one of the things, I don't have it on here. I lost a flash drive. I had a couple of nice things on it. I used it at somebody's house. I plugged it into their Mac, you know, because they said to me I could do that. And I plugged it into their Mac, and it worked okay there. But when I took it out, my programs were all scrambled. I couldn't, you know, I tried to put it in my PC again. The PC said, broken. You can't read it. So, well, one of the things here is the further and further you have these ropes get connected, the greater and greater the tension is. And in high school, one of the things I do to prove this to the students is we'll go out in the parking lot and I'll get a nice strong rope, okay, and tie it around a palm tree, okay, and then take the other end of the rope and tie it around somebody's car or a Jeep. Last time we did it was a Jeep somebody had. One of the students brought a Jeep over, tied it around the trailer hitch on the Jeep, and just left the Jeep sitting there with this rope. As long as the rope was straight, okay, I had the smallest student in the room just come and stand in the middle and just push on the rope. And when she pushed on the rope, the Jeep came right back. Okay? It's because there's so much tension in there that it causes it to move. A couple of years ago, I had a student here at Edison that said to me, I don't believe that. Okay, well, you know, he said, I'm going to do that with my dad when I get home. Because, you know, my dad's a mechanic, and, you know, I don't think, anyway, he went and recorded it. And that's what I lost, unfortunately, was his Cherokee or whatever it was that they had, and they connected a rope with it, and his dad was, you know, recording it on the phone, and he just pushed on the rope and came right back. Okay, a lot of tension in there. This is just an aside, but anyway, it's an interesting thing. I want you to realize that's why when they string like telephone wires or cable wires in the air, they never make them straight. They always let them curve a little bit because they can support more weight that way.
Was the Jeep in neutral?
I'm sorry?
Was the Jeep in
Yeah, it was
neutral?
in neutral,
Okay.
yes. Yeah, oh yeah. If it wasn't in neutral, then you wouldn't be able to move it at all. No, just sitting in neutral, but you push on it, and it comes right back, like a mile an hour or something. It'll move right back towards you. Very cool. Yeah, in the physics class, where they do all the math, where they have a problem there where they have a bird landing on a tightly stretched telephone wire, cable wire up in the air, the one that's tightly stretched, and the bird weighs, I don't know, 5 ounces or something, and the students show mathematically that breaks the cable because there's no way for the cable to support that little bit of weight. And to support that, it's going to take a tremendous amount of force in the length of the cable. It's just one of those things that that's just hard to believe. So maybe you want to try that yourself sometime. All right. Well, this is about springs. We already talked about springs. Okay, now let's get to your book. Example 3.2. Let's see. And it says, I think I probably copied it up there. No, not really well. It's on page 34. And it says, an orderly is pushing a gurney with a patient on it. The mass of the orderly is 85 kilograms, the mass of the gurney is 20 kilograms, and the mass of the patient is 50 kilograms. The orderly exerts a backward force of 100 newtons on the floor, pushing in other words. What is the acceleration? Now to do that, you have to know Newton's second law. You can probably see it here. Newton's first law, remember, said that the force, if the net force equals 0, that's his first law. Then there's either no motion or you're moving at a constant velocity and in a straight line. Okay, or constant speed in a straight line. If there is a net force, Newton's second law said then that will result in movement, and that movement will be the product of the mass of the object multiplied by how much it accelerates. It's going to be the mass times the acceleration of the two. Always. No exceptions to this. It's always true. So if we take a look at this gurney, well, you can see that in this case, using Newton's second law, you can see he's pushing with a force of 100 newtons. So you'd say, if you were solving this problem, you'd say, okay, the force that he's pushing on the floor is 100 newtons. The mass is going to be the three masses. The mass of the orderly, plus the mass of the patient, and the mass of the gurney itself. So you're going to add up 50 and 20, which is 70, and another 85, or 155 kilograms. So this would be 155 kilograms. And mass is always, in all of our problems, it will be in kilograms. All right, and then the acceleration, if you don't know that, we don't know what the acceleration is. I'll just leave it as A for right now. Okay, so then to solve this, you divide both sides by 155. Right, and they cancel on this side. So then the acceleration equals 100 over 155, which is, I guess I figured up there, 0.65. 0.65, God bless you. Then acceleration for us is always going to be in units of meters per second squared, or actually per second, but we write it per second squared. But that's what the acceleration will always be in. Meters per second squared. See, we skipped that chapter 2, so that's where some of this math first came up. All right, but you see how we figured out how fast that was going to accelerate? Okay, by using Newton's second law. Okay, so please stop me if you don't like it. Doesn't make sense. Okay. And then the next one is another part to this question in your book. What portion of the 100 Newton force is just on the gurney and the patient? In other words, not on the orderly. So for that, you say, well, we know that altogether, they're moving at this speed, because we just solved that. That's how fast all three of them move. But then that means what part of it is, of the 100 is going to be the, just the mass of the gurney and the patient, these two, times that acceleration. And in this case, it comes out to be 58. Maybe I should write that over here so you guys can see that. All right, 'cause now we know what the acceleration of the system is. We're not doing this one. So in this case, the force on the gurney and the patient, all right, these two, is now going to equal the mass of those two, which is going to be, what was it, 80 and 50, their mass, multiplied by the acceleration. We know they're moving at this acceleration. That's what we got before. So that's going to be that force. And that comes out to be about 58. So 58 newtons of the 100, all right, is that. You would say, well, then what is the force that's just on the orderly? Well, you can say, well, the orderly, his mass is, what was his mass? 70, no, 85 was it? I don't remember, I have to go back and look. Yes, 85. All right. His mass is 85, and that has to come, he's moving at the same acceleration, they're all going together, and when you figure the math out here, you're going to see it's just the other half of the 100 over here. So instead of 58, it's going to be 42. Because the two of these together have to equal 100. Okay? If I give you a problem like that on a test, you guys can do it? Nah? Okay, well, you want to think about it, and we'll start by going over problems next, in the next class, to make sure you guys get that, okay? I just wanted to show you, this is in the book, I just wanted to show you here that it's just going to be the combination of those two. So, okay. The second law, as it points out here, also gives you the difference between, using the second law, or rather the relationship between mass and weight. Mass and weight are really different things, because mass, this is the amount of matter that makes you up, or the amount of material. The amount of matter. This is the force of gravity. Force of gravity on the matter, like your body, for example. And the force of gravity on our planet, the force of gravity is always going to be, it's not, the book will tell you it's 9.8 meters per second squared. It's an acceleration that's due to gravity. It's how fast things accelerate when you drop them. In this class, if you want, you can round that to 10. That's okay with me. Your answers will be a little different than in the back if you do that, but I'm just thinking to make it easier for you. So, okay. So I just want you to realize that the weight is always a force. It's either in pounds, okay, if it's in the British system, or it's in newtons if it's in the international system. But it's always a force, all right? Whereas mass is a scalar. A mass is just the amount of molecules. Use the M to, to your advantage there and help them to remember this. Matter, molecules, material, whatever, but that has nothing to do with with gravity. Okay. But I want to show you that also falls out of Newton's second law. The same the force equals the mass times the acceleration. Okay, or as it says here, your weight is the force, depends on gravity. For example, like I said, I weigh 180 pounds here. If I were to now be on the moon with the same scale, and I stood on the scale, and I tell you, well, the acceleration of gravity is not the 9.8 or 10 like it is here. It's 1/6 of that amount. So how much would I weigh on the moon? What do you think? If I weigh 180 here, and now gravity suddenly becomes 1/6 of what it was, what would I weigh? What do you think? What's, sorry? Yeah, it'd be 1/6 of that, or 30 pounds. I looked at it together. Whoa, I really lost a lot of weight. All right, I'm down to 30 pounds. All right, it's because, but I'm still here. All right, all the molecules are still here. Right, the pasta I had for dinner. I mean, everything is still here. Okay, nothing's, the amount of mass is the same. It hasn't changed. So weight is really dependent upon what the acceleration of gravity is. Okay, it depends on it. So if you go to Jupiter, Jupiter has, I've forgotten now, but several times the gravity of the Earth. You really be heavy. You feel very heavy on Jupiter, but that's because it's such a big planet. Getting back to Newton's law of gravity. Okay, but I want to make sure you remember the difference between weight and mass. If I ask you that question, you guys can figure that out? Okay, good. Now, torque. Torque is the product of a force multiplied by the distance that the force is applied from some point of rotation. Like on this door, or you go to Dillard's, or you can go anywhere, the mall. You got these doors. I think you guys know that if I get far away from the hinges here, right, it's easy to open this door. Only a little force is needed to push this door open. But as I get closer to the hinges when I want to open the door, I have to push harder. Did you ever notice that at the mall? You might try that. You get closer, you got to push harder. Right? And the closer I get to these hinges, I got to push really hard to get it to open, because it takes a certain amount of torque to open the door. And what I'm doing by pushing like that is I am getting closer and closer to the hinge here. So in order to generate that amount of torque, maybe let me write that down here. It might be easier to show this in a diagram like this. Let's say here's the hinge, and say this is the door like I have there. And let's say the door is, what do you want to say, 3 feet? 3 feet from one end to the other. And let's say that the amount of torque that we need here is 100 units of torque. Okay, now, that means that using this formula that says that the torque is equal to the force that you apply multiplied by what's called the lever arm. Did I use that up there? Yes, okay. It's the distance that you are from the point of rotation. So, the lever arm. So, let's say I'm out here. So my force out here at 3 feet is going to be, I need to get to be 100. So that means I need a torque of 100, and I have to have a force right at 3 feet, but I'm 3 feet away. So can you guys see from this that the force at 3 feet is going to be about 33 pounds? For example, right, it's going to be 1/3. Does that make sense? Now divide by 3, both sides, right? Divide this by 3, divide this by 3. So we end up with about, I'm just rounding it here to 33.333. What are you guys saying, repeating or something like that? But anyway, you see that? Now, let's suppose I go to Dillard's and for some reason I can't do that. I have to push it here. Now, what's my force at, say, 2 feet? That's probably more like 1.5, isn't it? I mean, we go out here a little more and make these numbers nice and solid. The force at 2 feet, well, it's going to look the same as this, except, because we're going to use the same equation, I still need 100 units of torque to open the door. So now it's going to be my force at 2 feet multiplied by my distance, 2. So you see, when you divide both sides by 2 here, now the force that I have to supply is now 50 pounds. Going from 33 to 50. You see, is this starting to make some sense? And let's go to 1 foot. Suppose we went down here, like at the door there, the force at 1 foot, okay, same, we'd use the same equation. We'll say it takes 100 units of torque to open that damn door at Dillard's, okay? It's gonna be the force at 1 foot times 1. Guess what? You gotta push with 100 pounds. You know, in this example. I just want you to see how the closer you get to the point of rotation, if it requires a certain amount of torque, you know, to open the door, you're going to have to apply more force. You guys see that? And what's the converse of that? The further away you get, the less force you need. Right? This is why crowbars are long, for example, right? The further away you are, the easier it is to lift something heavy on the other side because of that, what they call that lever arm. So, okay. And that one I say force in newtons, but that's okay. We can go back and forth with the units here. Seesaw. How do you balance on the seesaw? Can I make this now? How do we balance on a seesaw? It's because the torque in one direction has to equal the torque in the other direction. So, like I have up there, right, if we have the seesaw, right, balanced in the middle, right, you got one person here, and you got another person over here, let's say. Now, if you look at the distances here, I might as well use the same ones that I have. I have here 2 meters and 500 newtons, okay? This is 500 newtons here, and this person is 2 meters from the pivot point, and then this other person is 400 newtons. All right, so they're a little lighter, 400 newtons, and the question is, where do they sit so that you can balance? The way you do that is you just say, well, whatever the torques are pushing this way, they have to equal the torques pushing that way. So that when they're equal, they can just sit there, right? Or you can go back and forth, nice and easy. But in order to be in balance, the torques on either side have to be the same. So you would say, if I say here the torque clockwise must equal the torque counterclockwise, for example, and this is the point that we're rotating about. So if we look at clockwise, that means this way, the torque in this direction is going to be the weight, or the force, which is 400, times the distance, which we don't know. I'll just put x, you know, for that distance. But then that's going to have to equal the torque going counterclockwise this way. But we know that is going to be 500 newtons times, we know that distance is 2. Okay, but you see we use the same formula. We just used it as making an equality so that we could get it to balance. So then in this case, you divide both sides by the 400. And x equals, I don't know, whatever it is. Let's see, 400. And then this becomes 10 over 4, or 4 divided into 10, which is what, 2.5? 2.5 meters. Okay, would be the distance that you would have there. So this person, but when you think about it, you say, yeah, they're lighter. They'd have to sit further away. Right? Doesn't that make sense? The lighter person have to get further out. I don't know if you've ever, maybe you guys don't remember. You're too old to remember when you were little on the seesaw. Right? The thing is, the heavier people had to sit more toward the pivot point in order to make it easier to balance than the lighter people. This is probably the longest night we're going to have. Okay, this is a long chapter, okay, so it's not new, okay, this chapter is long. All right. This was a figure in your book on page 51. Let's just take a look at that. I won't kill you with that one if you guys think you can figure it out. Let's see. Oh yeah, this is biceps. They want to. That's what I did. That doesn't look very much like a humerus. But anyway, the point here is I just wanted to simplify it so you can just see where all the masses were and the distances were. So look at this, and I'll let you guys work on this yourselves, and we'll start by going over this next time, okay, to make sure you guys see it. But this is as complicated as it gets. But again, it's going to be the clockwise torques, these two, coming down, the counterclockwise one pushing up. And I wanted to point out to you that to lift a weight of, how much weight are they saying you're lifting here? I don't remember. I have to go through here and see. And I have to read the whole thing to find it. It's not obvious here. But it's quite a bit more. It's generally about 100 times the weight of the object. It's a lot. The book says 484 and or 494. It says 484. I must have rounded. But I did want you to realize that the problem here is, the problem comes about because you have a nice strong clockwise set of torques here pulling down, and now to your biceps, by pulling up, the biceps is actually very close to the beginning of your the forearm here. So you really only have just a little short lever arm. And remember, you saw with the door before, the shorter the lever arm is, the more force it's going to take. So your biceps actually lifts up a lot more weight that way. This is another reason why people have to learn. You guys will probably have to remind yourselves, because you're getting older now. And you know, little kids, when they go to pick something up, they go right down and pick it up. But when we get older, what do? We lean over when we pick it up, right? It's very bad. For the same reason that you're putting a lot of strain on your lower back when you do that. You have to learn to use our legs, and there may even be an example in the book. Yeah, there is an example in the book about that, if you want to look at that in more detail. But it's the same idea. You have to be very careful. You don't realize how much that force gets magnified. The biceps example is one that I'm pretty sure you can follow. And if you don't, we'll go over that first thing next time. So this is the end, I think. Circular motion. Remember I told you about Newton. He said, if the object is not moving in a straight line, you have to exert a force on it. There's no way that the object will turn unless you exert a force. So, what we have here is, if you have something spinning that's in a circle, all right, as it says here, Newton's second law says there must be an acceleration, and it will be toward the center. The object will be moving toward the center in order to keep turning it, in a circle as it goes around. You have to have a force that's constantly pulling it in. And this is, of course, if your car is going around a curve, but it's the tires that are supplying that force. If you're making a curve in this direction, all right, your tires are the ones that are making the car stay, turning in that direction. It's the friction between the tires and the road. Maybe when you were younger, did you ever go on, or maybe now, I don't know, if you go to Universal or something, did you ever go on the ride where I've forgotten what it's called, Gravitron? I don't know, it's like a big cylinder. And you get up against the back of it. Everybody stands around the outside like this, right? It's a big cylinder, and they start to spin it, all right? And when they're spinning it, they're being pushed this way. You can now lift up your arm, your legs can both go up and all. I mean, you can just balance yourself like this. Did you guys ever do that?
Yeah, that is the Gravitron.
What's that?
They still have it.
They still do. They're fun. What's happening there is this acceleration toward the center. It's called the centripetal acceleration. That's what's being supplied to your back. That's what's pushing you, okay, in that direction. If that wasn't pushing you, off you go, okay? If you were spinning something around over your head, all right, people used to think when they spun something around over their head and they let it go, all right, then it goes out. No, it doesn't go out. It goes in a straight line. In other words, if you were to let go of the string right here, right now, it would just keep going in the same direction it was going before. No difference. Exactly the same. But it looks like it's going out because it's going away from you. Because see, you're standing here, so you're seeing it go out there. So people used to think that there was something called centrifugal force pushing it out. There's no such thing as centrifugal force. The only force that there is centripetal, P-E-T-A-L, pulling it toward the center. And if you don't have that, it just, what did Newton say? Straight line, constant speed, that's it, that's what it will do. So you let it go, it'll just keep going in a straight line. But look how that fooled people for years, okay? Because they thought there was something pushing it out. There's nothing pushing it out. It's just you holding it in. You're keeping it going around. It's a whole different way of thinking. It's really very different. Still okay? All right. Here's another example of it, a washing machine. A washing machine is made up of a tub within a tub. And the tub that's in the inner one has slots or holes in it. Okay? Anyway, the clothes go in there and they get washed and all. When it goes in the spin cycle, okay, the objects don't want to spin. What do they want to do? They want to just keep going in a straight line. And so what they do is they tend to move toward the outside. This is why, after the spin cycle is done, did you ever wonder when you open the lid why all the clothes are around the inside of that tub? That's right, just like you and the gravitron, okay? That's what's holding them in, right there. Whereas the water goes through the holes and gets collected in the larger tub and pumped out. Okay, but that's how that works. It works because of what's holding the clothes in place is that centripetal force, just like you being held on that gravitron, pushing you in the back. I think this is the last slide, am I right? All right. The way a centrifuge works is the same way. The objects are trying to get away from the center, unless there's something to hold them in place. And in the case of a centrifuge, since the objects will have different masses, remember we saw that the force on them, that force that's moving them to the outside, but in fact, it's really the absence of the centripetal force. The thing is, we have here the force is the mass times the acceleration. Well, the masses will depend on how quickly or easily the objects will move. And that's why you get the red cells packed down at the bottom in the centrifuge. Then you have the white cells and plated-rich plasma, above that. But they separate out because of their mass. Okay, that's all. But they're spinning really fast, as you guys know. I've done this. And I think that's it. Is that enough? Yeah? Okay. Now remember, if you're having trouble with home and you can't get an answer to something, email me and then put it aside. I check my email every day, and I'll email you how to do it. Okay, the problem. Depending on the payment. Or just email. You don't want to worry.